Greetings. We managed to calculate some of the properties for our problem in the previous video, and now we continue with the rest of the properties. So, reading from the tables, what we have is that our point 2 with a good approximation is P2 equals 200 kilopascals and T2 equals 393.36 kelvins, and this is saturation, T2 sat. It is saturation temperature for this pressure, and V2 is 0.88568, which we assume to be a very good approximation to this value that we had. U2 is 2529.1 kilojoules per kilogram, and H2 is 2706.2 kilojoules per kilograms, and S2 is 7.1269 kilojoules per kilograms Kelvin. I encourage you to read all these values from the table, find them in tables, and ensure that you can also repeat this reading that I have done. Now, so we know everything about the points 1 and point 2. Now, what happens to point 3? I would prefer to draw this diagram again and tell you what happens to point 3. It often is good practice to draw a better diagram once we know the process and we know the properties, and then we are in a good position to draw a better diagram. So how I would draw it is this. You see, this is the our initial condition, which was 41.7 kilopascals, and we now know that at 200 kilopascals, which is not far away considering that this is 22,000 kilopascals, so 200 kilopascals would not be very far away from 41. We have our here, this is 200 kilopascals, and strange enough that if we draw it, our initial point would be here. It means that still this point should be far to the left, and in fact, you see this curve should be almost vertical and very fast coming down. So a point with, this point doesn't represent an x to be 0.23, but that's it. It's difficult to draw the process easily. So these are our points, and at some point 1500 kilopascals, which would be somewhere here, this is 1500 kilopascals, the piston would start to lift. And our process, as I mentioned, is like this. You see, since the mass is constant and the volume remains constant, point 2 is here, and it remains specific volume remains constant until the pressure increases to 1500 kilopascals, which would be point 3. This is point 2, and this is point 1, and this is our procedure. Green color is our problem, and the blue color are just steam properties. So now we have point 1, point 2, and point 3. Going to the tables, we would have little information about point 3 in the tables. Why? Well, simple to say, because point 3 is superheat, far from superheat, and it is now just like perfect gas. And perfect gas is a good approximation for it at here. In fact, just to learn how perfect gas would be a good approximation, let's have a look at this figure, which is from the book Senja. And you see that for 10 kilopascals, which is this line, saturated vapor just gives 0.1% of error. For 100 kilopascals, it gives 1.6% of error. And for 1 megapascal, 1000 kilopascals, it gives 7.6 and 25. So these points are in fact not good approximations for perfect gas. But for these points, perfect gas is a good approximation. Now, the other point is that if we keep the specific volume constant at 200 kilopascals, which would be somewhere here, okay, to reach 1500 kilopascals, which would be a line here, we would have to move very far up just to reach that point. So what we expect is a very, very hot temperature at point 3 when the piston will start to lift. So let's return to the problem, and what we know is that this point has a very high temperature, far above its far above the critical point, and at that point, the perfect gas would be a very, very good approximation. You see, at these points, perfect gas is a very good approximation. You see, at these points to the right of this dashed line, perfect gas is a very good approximation. And perhaps where we get would be somewhere near this line. Okay, somewhere near this line, it would be a good approximation, and that's what we would try to look at. Now, so for point 3, our calculation would be that for point 3, we have point 3. We know that our pressure is P equals 1500 kilopascals, and V, a specific volume, would be 0.8855 cubic meters per kilograms. And therefore, if we calculate the temperature from the perfect gas law, then the conclusion we would reach would be PV equals RT, and therefore T equals PV divided by R, which is P 1500 times V, which is 0.88568. I would just continue using this value, and then divided by R, which is 0.4615. Remember that this is the value of R for steam, for water, and not for air. For air, this value would be 0.287, but for water, this R is 0.4615. And the temperature at point 3 would be 2878.7 kelvins. And as we expected, the temperature is very high, considering that the temperature here at the critical point is somewhere around 640 kelvins. Then 2800 kelvins is far high and far above there, and that's what we expected from the figure that we had, that just going at constant specific volume here would end up somewhere up there, uh, crossing the 1500 mega, 1.5 megapascals and 1500 kilopascal line. So we expected it to happen. It is correct. And now we know that this happens just at 2878.7 Kelvin. A question that was asked early in the problem was that if we place the plate with no weight, no resistance to pressure, and no resistance to temperature difference, if we place such a plate over the liquid, then where would that be when it's all vapor inside, after all liquid has vaporized? And to answer this question, now we need to take two steps. First, we have to decide where this plate was in the beginning, and then we have to decide where this plate would be at the second point. So we have to measure the mass of the vapor here. And the mass of the vapor is easy to calculate because mg, which is the mass of the vapor, is x times the total mass, the mass of water. This is by definition. And this is the definition of the quality, which is the mass of vapor divided by the total mass. And therefore, the mass of vapor is 0.23, which is the quality, and times 0.1515, which is the initial total mass, and the outcome would be 0.0345 kilograms. This value is the mass of the vapor here. You see, the vapor here has such a mass, and at the end, it would have such a mass. Throughout, this would have such a mass. Do we expect it to become smaller or larger? We expect it to become smaller, since this liquid vaporizes and it would occupy more space. Generally, this piston won't move from the beginning to the end, and therefore the total volume would remain constant, but when liquid vaporizes, there would be more space that it would require and it would occupy. So, at the end of the story, at condition 2, the this is the vapor specific volume, and therefore V2 would be 0.0345 times 0.88568, and this would be 0.0301 cubic meters. And what was the volume to begin with? V1 of the vapor, V1 would equal, once again, this mass, which is 0.0345 times 3.8419. Where did I get this value from? This is the specific volume for the vapor at its initial condition. And the answer would be 0.132525 cubic meters. You see, vapor occupied a larger volume, and at the end, its volume has become smaller since the liquid at the bottom has vaporized. The volume that we are calculating here is just this volume above this plate that we mentioned. In this problem, we need the properties for 4 points. Point 1, which is our initial condition. Point 2 is where all the water in the cylinder has vaporized. And point 3, where the pressure is 1500 kilopascals and the piston wants to lift. There's also a fourth point, which is as important, since we wish to talk about availability, then we would need to know the conditions at in the ambient, and we have to define the ambient. Let's say that ambient is P0 equals 100 kilopascals and T0 equals 15 degrees C or 288 kelvins. Now, if this is ambient and water in this ambient has properties, its properties would be saturated liquid at 15 degrees centigrade. It is compressed liquid, but we could very well approximate its properties from saturated liquid at 15 degrees centigrade. So at 0, which is ambient, V0 is 0.00101, and that is cubic meters per kilograms. U is 62.980 kilojoules per kilograms, and H is 62.982 kilojoules per kilograms, and S is 0.2245 kilojoules per kilograms Kelvin. I will talk about availability just shortly, but let's just put down the values that you have. At point 1, which was our initial condition, we calculated the properties and we learned that V equals 0.8855, U equals 817.6, H equals 854.5, and S is 2.56. At point 2, we calculated the properties, and they are here. At point 2, V was 0.885. Well, we approximated them that this change wouldn't be much, and we just accepted this value. It's good approximation. U2 is 2529.1. H2 is 2706.2, and S2 is 7.1269. So these are the values for point 2. At point 3, which is just up here, we have the properties. Well, V is the same, is 0.88568, and U we don't know because it is perfect gas, and we need to have a reference point just to have a value for U. And we have to be careful with that reference point. We can't just put it 0 Kelvin, because the reference point for U in these values that we have read from the table is not 0 Kelvin. Most tables place the reference point at the triple line, the saturated liquid at triple line, and they assume that U at that point is 0. So, and the temperature there is 0.01, which is almost 0 centigrade and not 0 Kelvin. So we have to be careful with these values and see how we can assume perhaps a difference between these two. There can be a good discussion on that point. Now, we have all these values, and now we can calculate the last property that we need, which is availability. What is availability? Well, you see, assume that this is the level of energy of some material that you have. Okay, this is the level of energy. This is the level of energy, level of present, level of energy. But how we judge this? Well, at least we know that there is a 0 Kelvin, and we could say that this is the total energy. This distance would be the total energy. This distance would be total energy as compared with 0 Kelvin. Okay, but we don't have 0 Kelvins, and so you can't use this energy. If we define it this way, I mean, in this way, everything has energy, but it's not useful. So what we do is that we define an ambient. This is an ambient, and therefore this is energy as compared with ambient. This is energy as compared with ambient. Okay, energy as compared with ambient. Now, the second law of thermodynamics tells us that not all of this energy could be turned to work. So there's part of this energy which is unavailable energy, and this part of it which is available energy. Now, this part, this part is what we are concentrating on. This is the part of energy. This is the part of energy which I hash with red, and this is the part of energy that could be turned into work. This is the part of energy that every material could have, and that part could be turned into work. A simple equation for that energy is drawn in just every textbook, and what we have for it is that A, which is that energy, is U minus U0 plus P0 times V minus V0 minus T0 times S minus S0. There are two other sources of energy which could be turned to work, and that is plus V squared over 2 plus GZ. So this is the maximum possible work that one could extract from a material in a very imaginary process. Look, this is an imaginary process. You don't need to do that process in order to have availability. Your material has availability, and it could be calculated in this way. And the meaning of it is that this is the maximum possible amount of work, which is in itself impossible, because if you could do that, all those imaginary processes should be reversible. But this is an imaginary item. This is a reference item. Now, this is availability for whatever there is inside your um, your boundary. Okay, and there is another availability which is flow availability. That we denote by AF, and that is H minus H0 minus T0 times S minus S0, and also plus V squared over 2 plus GZ, and that is flow availability. And if you want to know how would you distinguish between these two, wherever you use U, its availability is A, and wherever you use H, its availability is F. So you always, it's good to remember that U and A come together, and H and AF also come together. This is how we calculate availability. You see, availability is a property since it's calculated from some sort of manipulation, some mathematics of other properties. So it is a property itself, and it is measured relative to ambient. Now, what is the availability for ambient? That is zero, because that is the dead state. That is zero because it is where there is no availability and your material is at rest with its surrounding. Now, let's calculate availability for point 1. A1 equals, we just replace values for this equation from this table, and it is 817.6 minus 62.9, 80 plus 100 times 0.88568 minus 0.001001 and minus this term, which is 288 times 2.56 minus 0.2245. And the outcome for A1 would be 170.46 kilojoules per kilograms. The unit is kilojoules per kilograms, just like U and H. And so here we could insert 170.46. As for point 2, A2 equals 2529.1 minus 62.9, 80 plus 100 times 0.88568 minus 0.001001 and minus 288 times 7.1269 minus 0.2245. And the outcome for A2 would be 566.7 kilojoules per kilograms. It's expected that availability would increase since we are heating the water inside our cylinder. So this would be 566.7, which is the availability for the second condition. Now that we have finished calculating all properties, we are now in a position to move to study the processes. Cheers.